Production is down, customers can't log in. Kubernetes is healthy, Docker containers are running, DNS works perfectly fine. TCP also connects, yet nobody can access the application. Why? Today, we are going to solve this production incident, and by the end of this video, HTTPS will never feel like magic again. If you are new to my channel, hit the like button, subscribe, and comment networking if you are following this series. Last episode, we learned TCP. TCP only creates the connection. It doesn't prove who the server is. Imagine someone calls you just because someone answered the phone. Doesn't mean it's your bank. HTTPS exists to answer one question. Can I trust the server I am talking to? Alright, let's jump into the terminal and build HTTPS by ourselves. First, I'm going to create a directory called HTTPS demo, followed by I'm going to jump into that directory. In this directory, I am going to run a command called OpenSSL. So what exactly we are trying to do here? So X509 is nothing but creating a self-signed certificate, followed by new key RSA2048. That means generate a new RSA key pair. Then we have nodes. Don't encrypt the private key with a password. This is, let's say, useful for demo, but not always ideal for production environment. Then we have a key out which saves the private key, followed by we have an out flag which is, let's say, creating the saving the certificate here. Validity is, let's say, 365 days, and subject CN is, let's say, local host because we are creating it by ourselves. I'm going to press enter. Now let's look at the files. So I'm going to say ls-lh. It will give all the details about the files with permissions here. We can clearly see two files. One is a certificate.cert and the second one is a private key. So after running that command, we generated two things. One is, let's say, the certificate. So this particular certificate contains public key, owner details, expiry, and issuer. And we have a private key. Never share this private key. Never share this private key. If stolen, someone can impersonate your server. Always make sure this particular private key has 600 permissions. In production, this particular file should only be readable by the service account running the web server. Now, let's jump back to the terminal and I'm going to change the permissions of this particular private key real quick. Followed by, now let's try to look what exactly we have inside the certificate. Now let's look at the details of what we have inside this certificate. I'm running OpenSSL X509 in certificate.cert text hyphen no out. Press enter. Now let's look at the fields that are important to us. For example, we have a subject CN which is equal to localhost. That means who owns this certificate. Followed by we can see the issuer. Again, if you notice, it is the same value localhost because we signed it by ourselves. Then we have the validity section. In this, you can clearly see not before, not after. This is where real production outages happen. Imagine if this particular certificate expires tomorrow, what exactly will happen? Let me know in the comments what exactly will happen if this particular certificate expires tomorrow. Followed by, if you see here, we can see the public key details. I'll try to scroll down. You cannot see anything related to the private key information. Now, let's try to inspect the private key details. Now, let's try to inspect the private key details. For that, I'm going to use OpenSSL RSA-in private key check. This is our private key. This never leaves this server. If GitHub contains this particular key, rotate it immediately. In real production environments, you are going to use something like key vault. You are not going to share it directly on the GitHub repository. Now let's actually start our own HTTPS server. I'm not using Nginx or Apache because I want to focus on the TLS part. So we are starting a simple HTTPS using OpenSSL, followed by we are using the certificate which we generated with a private key, and we are telling it to accept on port 8443. Press enter. Now if you see, the server is now waiting for incoming HTTPS connections. Let's leave this terminal running and open another one. I'm going to open this terminal, and in this terminal I will say curl https localhost 8443. Press enter. Look at this. We can see an error SSL certificate problem self signed certificate. The server did send us a certificate. The TLS handshake started. So here's the question. If the server sent a certificate, why doesn't curl trust it? The answer is simple. HTTPS isn't just about sending a certificate. The client has to decide whether that certificate can be trusted. Our certificate is self assigned. That means it wasn't signed by a certificate authority that the operating system already trusts. So, this curl receives the certificate, checks who signed it, can't find a trusted CA, and immediately stop the connection. If you look at the server terminal, you will even see TLS V1 alert unknown CA. This message came from the client. It's basically saying, I received your certificate, but I don't trust the authority that signed it. Nothing is wrong with TLS itself. Encryption worked. Handshake also begin. The only problem is trust. Now watch what happens if I tell the curl to skip this. I'm going to add a flag here. Press enter. This time the connection succeeded. Not because the certificate authority suddenly became valid, but because we told curl don't verify whether this certificate is trusted. And that's exactly why using -k in production is dangerous. It hides certificate trust problems instead of fixing them. Please do not use this in production environments. So far, we did create our self-signed certificate. Now let's try to discuss about the actual website google.com certificate. I'm using OpenSSL S-Client Connect google.com here. Show certs. Press enter. If you look at the top of this particular certificate, here I can see three different depths. One is depth 2, verify written. Depth 1, again verify written 1. Depth 0, verify written 1. This is OpenSSL showing the certificate chain. If you look at the depth 0, This is the actual website certificate. This is Google certificate. If you see, cn is equal to star.google.com. Now, if I scroll down a bit and look here, this is depth 1 intermediary certificate authority. If you see, Google Trust Services, and the CN is WE2. Followed by, if I scroll down, we have another depth. Depth 2 is the root certificate authority. Google Trust Services LLC, followed by CN is equal to GTS root R4. So the chain looks like this: root certificate, followed by intermediary certificate, and then finally we have the actual website certificate. This is why the browser trusts Google. Now look at this particular section: server certificate, subject equal to cn star.google.com. This tells us this certificate belongs to star.google.com and it was issued by Google Trust Services. That means Google did not create a random certificate by itself. A trusted certificate authority issued it. Now look at the most important part here: verification equal to OK. Verification return code 0 OK. This means OpenSSL successfully verified the certificate chain. The certificate is not expired. Certificate actually matches the domain as well. The issuer is trusted, and this particular chain can be followed back to a trusted root certificate authority. This is the difference between our self-signed certificate and Google certificate. Our certificate said, I'm valid because I say so. Google certificate says, I'm valid because a trusted certificate authority verified me. This is the real trust behind HTTPS. Now let's talk about a real production incident. Imagine it's Friday afternoon, everything is healthy, pods are healthy, your CPU, memory, and all looks normal, but users cannot log in. And you try to run this command, which will give you the information about the certificate. And if you look here very carefully, not before, not after. In our incident, this date had already passed. The certificate expired, browser refused the connection. The application will never even receive the request. How will you fix this? Let me know in the comments. And few more interview questions. Which file should never leave this server? If you know the answer, again, let me know in the comments. Private key. And also, can anyone create the certificate? Yes. Why does curl-k work? Because it skips the certificate verification. And finally, why doesn't yeah, why doesn't the browser trust ours? Because no trusted CA signed it. Before we end, let's put everything together. When you type a website in your browser, all of this happens before your application receives a single request. Let's walk through it one last time. Where is the server? DNS answers. TCP answers, can we establish a reliable connection? TLS will answer, let's create a secure channel. Certificate answers, here's my identity. Trust answers, can I believe that identity? Encryption answers, now nobody else can read our communication. Only after all of that, HTTP can finally send the request, and only then application receives it. This is why a production issue that looks like an application problem can actually be a DNS problem, a TCP problem, a firewall problem, certificate problem, or a TLS trust problem. As a DevOps engineer, our job isn't just writing deployment pipelines, it's understanding every layer between the user and the application. Because when production goes down, the application is often just where the problem becomes visible. The root cause is usually somewhere underneath, and now you understand exactly what happens before your application sees a single HTTPS request. In the next episode, we'll answer another production question. If you enjoyed this episode, hit the like button. It really helps this series reach more engineers. Subscribe if you haven't already. Thank you for watching. I'll see you in the next episode.